Okay, so I think we should make a start. So I started talking about this last time, but I'm going to somehow recall where we were. So this is about the Zilber-Pink conjecture for a curve in y1 cubed. All right, so let v in y1 cubed be a curve not contained in any proper, as a subset, special subvariety. So that means there's no modular relation on two coordinates that holds identically, and no coordinate is constant and special. And this is the right hypothesis for this problem, and then in this case, the Zilber-Pink conjecture predicts that there are only finitely many points let's call them x, y, z in V. Only finitely many points of V lie on a special subvariety T with the dimension of T equal to 1. So this is an unlikely intersection because V is a curve and T, the special subvariety, is a curve, dimension 1, and we're in an ambient of dimension 3. So that's an unlikely intersection. And such T, the special subvarieties, take a few different forms. So one way to be a special subvariety of dimension 1 is that you fix two coordinates special and then just take the line on the other coordinate. So let's say two coordinates special. Another way is one coordinate special and one modular relation. Let's say x. Say x is special and one modular relation on the other two coordinates. One modular. And the other way, which is in some sense generic, but somehow where you simply have two modular relations, in other words, that the coordinates are pairwise related by modular relations. And as I mentioned last time, if x and y have a modular relation and y and z have a modular relation, then that will entail x and z having a modular relation too, and there'll be some relationship between the three indices L, M, and N. Let's call them that the third one is always less than the product of the other two, and so it's really enough to consider two of them. Now I want to make some remarks. So if two coordinates is special, then we're really talking, if you project the curve onto those two coordinates, you're simply talking about the Andre-Oort conjecture. And so these are finite by the theorem of Yves Andre. So this type 2, we'll see that some results of mine with Philip Habegger make this finite. Habegger Pila. And this type 3, there are some partial results which I'll explain. But this is in general open. There are some partial results due to Habegger and me, to Dor and Ohr, and to Papas. So I'd like just to say something else at this point. I've taken a curve in y1 cubed, but I could have taken a curve in y1 to the n for it's almost no different, because the special relationships only involve 3 or 4 of the coordinates anyway. So if you do it in y1 to the n, you just have a sort of a management problem on these extra coordinates. There's something very slightly new in that you can have 2 pairs of coordinates that have a modular relation, that are 4 coordinates instead of 3. But it's really not much different. So let's say this, I've taken it in y1 cubed because it's easier to write x, y, z. But there's really there's nothing much else going on.
You're saying for a curve or?
For a curve, yes, sorry. Of course, for higher dimensional things, there are similar things going on, but there are much fewer results. All right. So I'm going to sketch a theorem, I'm going to sketch a theorem which is essentially what I proved with Philip Habegger. And there's a key sort of arithmetic ingredient So as in the case of Andre-Oort, when you do this counting approach, somehow the key thing at the end turns out to be that the points you're looking for have a lot of Galois conjugates. And so I'm just going to put this out there now and then go through the proof, and then I'm going to come back to talk a bit about this conjecture. So here's the conjecture. So given curve V in y1 cubed, which is defined over some field. Oh, goodness. All right. They became defined over a field L of finite type. There exist constants C, let's say, depending on V and L, and delta depending on V and L, positive, such that for T special, and the dimension of T is equal to 1, and if X is a point in V and T, then this point X has a reasonable Galois degree over the field of definition. And that will be that it's at least this constant times the complexity of the special subvariety to the power delta, where there's C in delta. And we, just to recall, that this complexity delta T of a special subvariety in y1 to the n even is the max of all the d's and the ni's. Well, let's call the modulus, the absolute value of the di's, where some coordinate is special. Xk is equal to sigma I, let's say special, or sigma k, where the discriminant of sigma k, absolute value is this, where dk is the discriminant of the special point, the discriminant of the order of the, we defined that, and let's call this and j, or you have some modular relation between where these relations define the special, right? So there could be 2 or 3 of those if you like, or there could be 1 of those and 1 of those, or 2 of those. And then you just take all the d's and the n's and you just take the maximum. Now, I wanted to say about this that when you do the Andre-Oort conjecture, the points you're looking for are algebraic. And so there's no point in thinking about varieties that aren't defined over the algebraic numbers. Because you can immediately assume that V is defined over the algebraic numbers. But here, it's not the case. The points you're looking for are just these intersections. So even if the curve isn't defined over the algebraic numbers, it still could intersect special things. And the best you can say really is that these points are algebraic over L, because they're in a finite intersection. All right.
Is there a strong belief in favor of the conjecture?
I'm sorry?
Do you believe is it true?
Yeah, I do believe it's true.
Or is there some proper evidence? Or?
I'm sorry? Oh, evidence, yes. So we'll come to that. I want to talk, about the theorem first. But then, actually, yeah, I've got a lot of discussion about that. We can see whether you think that's evidence.
And remind me, is there some argument saying that if you know the conjecture for V defined over Q bar, then you know it in general for this Zilber-Pink kind of question? I remember something like this, but I'm not sure.
So I'm not sure exactly what Barroero and Dill. It may be, but you may need to know it generally over. Okay, I don't remember exactly. There are some results that might say if you know Zilber-Pink for everything in Q bar, then right. But there are some other results that say it's enough to know it for the same kind of thing. Actually, I'll explain at some point also that, you can prove this. I did prove this when V is not defined over Q bar. That's part of the evidence, in a way. And because that comes down to proving, that comes down to the gonality of modular curves, somehow. And maybe I could say at this point also that if V is, so to speak, strongly not defined over Q bar, if V is Q bar Zariski dense in Y1 cubed, then this statement follows from the theorem I mentioned of Chatzidakis, Gioja, Massa, and Morin, that the Zilber-Pink setup holds for varieties over C with respect to varieties over Q bar, considered as special. So in the case that the V is Q bar Zariski dense here, then there are only finitely many intersections of V with curves defined over Q bar, even not special ones. So it's the intermediate case which is kind of interesting, where V, the curve V, if you like, has one equation over Q bar, so it's not unlikely with respect to that problem, but it's not defined over Q bar. But I'll come back to all of that. I'll come back to all of that. But I just wanted to sketch the counting argument that this is somehow the input it needs. So that's what I wanted to sketch. So let me write that down back over here. I'm going to use the middle boards. So that's the theorem, and that's with Philip Haberger and me, that says if LGO holds, for V, then Zilber-Pink holds. All right, so I've just put that conjecture out there, over there, so that I can sketch the counting argument. Of course, that'll turn out to be the key thing, and I want to then talk about the evidence and some related conjectures. Now, also, I'm going to make an additional assumption for now. Assume that V is not contained in any proper weakly special subset. Oh, goodness. Weakly special subset. So, of course, this is a stronger hypothesis because there are more weakly specials than specials. Now, you may, if you're weakly special but not special, that means that there's a coordinate which is constant on the curve. The weakly specials are allowed to have any constant. A constant coordinate can be any constant, not just special, whereas the special subvarieties, any constant coordinate has to be special. So the difference here is that there may be a constant on V, there may be a coordinate which is constant on V, but not special. And that turns out actually to make the problem easier, but I want to deal with that somehow as we go. It'll become clear when we talk about isogeny estimates, why that's a kind of a much easier case. And so for the moment, it's convenient to assume this stronger thing. All right. So we're going to count rational points on something. So I'm going to sketch the proof. And we'll see the various other ingredients that come in apart from that main one. So I'm going to let Z be the inverse Cartesian product of the J function on V, intersected with the fundamental domain. So let's just I'll draw the picture. This is the fundamental domain of the J function on y1 cubed. And that maps down to y1 cubed, in which we have our V. Okay, so this is going to give, and this is a definable set in an O-minimal structure. However, when you intersect V with, so there's, let's say, V with T, and that's going to intersect in some points, those points aren't special. They are some points defined over L bar, but they're not special points. And so the pre-images of those points are not going to be rational points or quadratic points or anything nice. So we're not going to count points on Z. And I'm going to consider these points of this third type. So I'm going to, so X will be, oh, now I've got X1, X2, X3. All right. I have to stick with my notes, otherwise it's very dangerous. All right. And this will be in V intersect T, and I'm going to have T will be defined by some modular relation on X1, X2, and a modular relation on X2, X3. These are these define T. I mean, these may not define T as an irreducible right? There'll be this intersection could be reducible. T will be some component of that, but we only need to know about the n and the m to feed into the complexity bound. And we know there'll be some third relation, which again we don't need to worry about because this L is bounded by n times m. Right. And now for alpha beta in GL2R with positive determinate, I define Y alpha beta to be the set of Z's, Z1, Z2, Z3 in the upper half plane cubed, such that Z2 is alpha Z1 and Z3 is beta Z2. So that's the usual action of Möbius transformations on the upper half plane. And this is a definable family of sets. It's, I mean, right, because this is, it's even fully definable in the semi-algebraic structure because GL2R is a semi-algebraic set. And given alpha and beta, you've got this relation, which is purely semi-algebraic. So this is a fully definable family, even in the nicest possible structure. And these all have complex dimension. They're all complex one-dimensional things. And then I'm going to take X to be the set. So these are all one-dimensional things. So again, you might expect that they wouldn't intersect this Z. This is also a one-dimensional complex thing that's a bit cut off. It wants to be periodic, but we've cut it off at the fundamental domain. So I consider the alpha betas in GL2 R, for which Y alpha beta intersects Z is non-empty. So that's a definable set because this is a definable set and that's a definable family. And it'll be on X that we can count rational points. So we can just, so if Z is J inverse of X, with X belongs to T, there exist alpha and beta in GL2RQ with Z belongs to Y alpha beta. And I'm going to just be a little bit more precise about that now. But that means that if we have a point that's in V that comes from a point in a one-dimensional special subvariety T, then there will be rational matrices alpha and beta for which we get such an intersection, so that the points we're looking for are going to give us rational points on this set here. So that brings me to the height ingredient. So let's call this the height ingredient. Because, again, as in the Andre-Oort setup, it's not enough to get a rational point. You have to have some control over its height, because we're going to count points up to a given height. So what is the height of that alpha beta? So this is all terribly classical stuff, but if G is in GL2Q plus, you can scale it to a matrix G prime, which is just a 2 by 2 matrix of integers with relatively prime entries, and then the determinant of that matrix we'll call the n of G. So you're given G, you scale it, you scale the rational numbers till they're integers relatively prime, and then you take the determinant of that and you call that n of G. And in that case, J of Z and J of GZ satisfy that modular polynomial. And conversely, if you have a point on the modular curve, then you can find a matrix of this form with that relation on the pre-images. So if you like, so there exist n and m. Oh, sorry, there exist alpha and beta with n of alpha is equal to n and n of beta is equal to m, where these are the n and the m here, n and m. And right, so that's telling me what the determinant of this matrix is, but not its height. And the other point is that we also want to take the pre-images to be in the fundamental domains. I want to take x1 here, x2 here, and x3. Everyone has a pre-image in the fundamental domain, and I know they're going to be related by a matrix, which when scaled you get these determinants n and m. So there's a proposition which is, again, very elementary proposition, which, well, Philip and I proved in a weaker form, and then this is from Massa and Zanya. Did it with a much better exponent. So let x1 and x2 be in y1. Oh, with a modular relation. For some n, at least 1. And let z1 and z2 be in the fundamental domain. So these are pre-images, the zi's are pre-images of the xi's in the fundamental domain. And then the statement is then there exists alpha and beta, which are 2 by 2 matrices with integer coordinates relatively prime, which do what we want. The determinant of alpha is n. Z2 is alpha Z1. And the height of alpha, meaning that the maximum of the entries, is bounded by some absolute constant n to the 3/2. So that will be sufficient somehow, because it means that from the complexity of your point, you're generating rational points whose height is bounded by a power of that.
What is beta here?
Yeah, there's no beta here. Yeah. You can do alpha, then you can apply the same proposition with x2 and x3, and you'll get a beta. Thanks. Yeah, there's no beta there. But you can also, right, so also the height of beta will be less than cm to the 3/2. So I don't want to say too much about this. It's very elementary somehow. This is terribly classical. One knows exactly what these matrices look like. So somehow a key point in doing this is working out, if you're a point in the upper half plane, what is the height of a matrix in SL2Z that you need to bring back into the upper half plane. Because if you're given one of these points, you can sort of write down SL2Z representatives, or representatives modulo SL2Z for its for the other points in the modular relation. That's I mean, right, that you just, there are these standard matrices that do it, finite number, but they will, of course, give you an x2 that's not in the fundamental domain, and then you just have to work out how expensive it is to bring that into the fundamental domain. And if you look at the very simplest proofs of how to do that, say in Serre's book on arithmetic, he'll tell you just the proof that that really is a fundamental domain, and you look at the matrix that brings you in and you just get terribly elementary bounds. Okay, it gets bad if your imaginary part is very small. You may be, but it's bounded essentially. Right. So this is very elementary. It's one of those things that becomes less elementary when you go to more complicated Shimura varieties, and becomes a problem in reduction theory, again, because the description of the fundamental domain and all these things are a bit more, much more intricate. So this is good because this height, if you like, is some fixed positive power of the complexity of the point we're getting, and so we are in good shape there. Right. So my next claim, maybe I better put it over here. So the claim is that each of these intersections, y alpha beta with z, is finite. I'm going to sketch a proof of the claim. But again, so each of those intersections is a definable family of sets, and definable family of intersections. And so again, the minimality of the families immediately implies that there's a uniform finite bound on the sizes of all those sets. And let me sketch the proof. If not, being definable, the intersection contains a positive dimensional real cell. That's directly by the O minimality. It can't somehow be some infinite sort of discrete set of points. If it's not finite, it has to contain a real cell, a continuous real locus. On the other hand, they're both complex analytic sets, so then it has to be then that intersection is complex analytic set. It's positive complex dimension. On the other hand, well, these are two one-dimensional. So y alpha beta is a one-dimensional, one complex dimensional set. So if the intersection of that with z is one-dimensional, this z is also one-dimensional. It's the pre-image of a curve. And so that tells us that the pre-image of v, at least that component, is contained in y alpha beta. some component. Because you've got a piece of V, this intersection is just one complex dimensional. And now, so is somehow the functional transcendence ingredient comes in. So this is something that you might call modular X logarithms. Because we've got the pre-image of an algebraic set under this highly transcendental function is now contained in an algebraic, something algebraic. So this is modular X logarithms, which in this case is a consequence of Mordell-Lang and Andre-Oort theorem, which simply says that if a component, or let's say if J inverse V is contained locally in some proper, as a subset, algebraic subvariety of H cubed. Well, that can only happen if V is contained in a proper weakly special subvariety. Okay, now certainly if V is contained in a proper weakly special subvariety, meaning that either some coordinate on it is constant or there's a modular relation on two coordinates, then the components of pre-images will indeed be contained in either constant coordinate in the upper half plane or a GL2R, in fact a GL2Q relation. So this is certainly a necessary condition. And this just holds generally. I mean, that theory for every Shimura variety and mixed Shimura variety. And one can, I call it X logarithms because it's an analog, if you like, of the independence functionally of logarithms. It follows from X-Shanwell theorem, if you like, that if this were the X inverse of a variety in C star to the n, so to speak, if you take the logarithm of an algebraic variety, that will be Zariski dense unless there is some multiplicative relation satisfied here. And then you would get a linear, a weakly special in C to the n, meaning some translate of a rational subspace. And this is the analog. It's playing the role here of the Ax-Lindemann theorem that we had in the other direction. And they both, of course, are special cases of a full Ax-Shanwell theorem for these uniformizing maps, which I haven't been saying much about.
In this case, you seem to use very little, just that the image of y alpha beta is closed if and only if alpha beta are in.
Yes, I guess that's right. Yeah.
You don't need at the end it's the same thing. But
I guess that's right. It's a simpler thing, but somehow, yeah, if you view this problem as a prototype, then you want that theorem. Right. So, and then, of course, if you remember, I've assumed for the moment that we're not contained in any weakly special subvariety, so that's just excluded. So this is excluded. Right. So now we can somehow get more to the conclusion of this argument. So now we have this point x, which is in V intersect T, the one-dimensional special, and it has at least on this assumption, it has at least the complexity of the special to some power conjugates, which again lie on V. So giving that many points, so we get the complexity of T to some positive power rational points on X, whose height is at most the complexity to the 3/2. I'm kind of leaving out constants, positive constants. And so that is, if you like, the number of points is some positive power of the height. And so if you have a point of large height, of large complexity, then you must start to see algebraic subvarieties in this set X. So let's just say the rational points lie, if you choose a suitable epsilon, which is smaller than those things, h to the epsilon blocks, let's say delta t blocks, which is connected semi-algebraic pieces of X of a particular form. Now you may remember also, I mentioned this just at the end last time, that this set X, which I think I may have unfortunately erased, but this set X is fibered by stabilizers, right? Because these are the points alpha beta such that y alpha beta intersect z is not empty. But if you have a point that's in that intersection, you can modify alpha and beta by stabilizers of those points. And so you'll generate a positive dimensional algebraic set that's inside X. Every time you get one point, you'll get a whole product of stabilizers. And so X-alg is actually the whole set. So if you were excluding the algebraic part and counting, you'd see nothing at all. But here the point is that you get very few pieces. And if these pieces that you get lie inside stabilizers, then they only account for one point. They only account for one of those conjugates. But we've got a lot of conjugates to account for. And the conclusion is that these blocks that you get can't, so to speak, all hide in stabilizers. At least some of them have to move outside of stabilizers.
And why all these points give different alpha betas? Why you cannot have a lot of points giving the same alpha beta?
Because they're bounded. The intersections are finite. So so each alpha beta only gives you finitely many. You've got a small number of blocks. So one of these blocks has to be giving you a lot of points. And so in particular, they can't all hide in these stabilizers. Now, there's quite a bit of again, administration at this point. So what you can do when you have this kind of thing, each intersection is finite, it means you can parameterize that I can choose finitely many functions on X, definable functions, that parameterize those intersections. Intersection number 1, intersection number 2, right? And then I can look at those functions and they'll be continuous outside of a definable set, smaller, and they'll be differentiable. And I can actually find, with enough minimal administration and known very basic results, that you actually can find some semi-algebraic curve in X with an intersection that moves. Then that's what you really want. And you can, so the O minimality helps you a lot there. You get a semi-algebraic curve, a real semi-algebraic curve, right? So real dimension 1 of y alpha betas for which the intersection with Z moves as you move the parameter. And so it's positive dimensional, positive real dimensional. And again, that's because there's a lot of, between here and here, there's quite a lot of, minimality is helping you out a lot because you can, the intersections are finite, you can parameterize by functions. Those functions will be very nice outside of smaller sets and so on. Once you get this, you complexify the parameter, of this real semi-algebraic curve. You'll get a complex algebraic curve. So now you get a complex algebraic, one complex algebraic dimensional family of these y alpha betas that move and that contain at least something real positive dimensional. But again, the intersection, complexify the parameter and take the union of the y alpha betas. This is now a surface, complex algebraic surface, and its intersection with Z is again complex, is a complex analytic thing that contains a positive dimensional real thing, and so it contains a positive dimensional complex thing, and so it contains V, the preimage of V. Locally, this is a surface, let's call it algebraic surface W, which is the union of these y alpha betas along this one complex parameter family that contains J inverse V. And now the theorem, the modular X logarithms kicks in again and tells us that that's now a contradiction because it implies that V is contained in a proper weakly special because we built a relation. This preimage is contained in something. All right, so that's somehow so again, and that's why I wanted this weakly special. The no weakly special assumption is what ties in with the functional transcendence, with the modular X logarithms. So that's what you want somehow. And I'll come back. So this means that the delta T, if you like, is bounded. A large complexity intersection simply generates too many rational points, and you must have all this, the intersection that moves, and then you get a contradiction. Right. So that, I guess, was the conclusion of that proof, except I'm going to come back to the weekly special. I mean, at that point, we'll come back. But are there any questions on this? I mean, that's sort of the end of the counting aspects of minimality, pretty much. Now I want to talk about this conjecture and isogeny estimates.
You probably said it, but you have a kind of Northcott property for the complexity, so that T-bounded implies only finite.
Yes, absolutely. Yes, I should have said that. With T bounded, that means that the well, in this case, the N and the M are bounded, but also the discriminants. And so that means that, everything is bounded. So actually, maybe this is the good time to take a break and before talking. So we'll break basically until, well, just after past. Rather than start, then I'll talk about these conjectures. Yeah. Okay. So let's resume. So I want to talk now more about these arithmetic issues, and so the first thing maybe to say. So I put this conjecture out there because it means we can just complete the whole argument, and that's the main arithmetic thing that you need. But it's sort of a bad conjecture. And the reason is, or one reason is, that if Zilber-Pink is true, then this conjecture is true because it's a conjecture about finitely many points. So it's a bit tautological. It is what you need to complete the argument, and it is what you can get in some cases, but somehow the real conjecture you want, but it's a bit artificial, okay? It's what you need, and then you can look at stronger things or weaker things. But a more meaningful, though very much stronger conjecture has to do with likely intersections, not unlikely ones. And this is, in analogy with the multiplicative case that I'll talk about a little bit. So here we would let W be a curve in y1 squared, not y1 cubed. Or maybe I should take V. Here I can see I've V defined over L, a finite type. Here the key case really is, let's just take Q bar. Well, let me just leave that. Okay. Then you have again constants C and delta such that if xy is an element of V which lies on a modular curve, then L of xy, the degree, is at least Cn to the delta. So this conjecture really is very much stronger, okay? Because this is dealing with a likely intersection, not an unlikely one. And these intersections are always going to be infinite, well, unless V is some shift of a modular curve, right? Unless V is, whatever, phi of n is equal to 3 instead of 0, something. In fact, it's probably infinite even then. So that's, if you like, it's much stronger conjecture. On the other hand, let me write this conjecture with a question mark, because it's even possible that you could have this kind of bound without the curve being there at all. So let's just write this down. There exists C and delta, positive constants, such that for any xy algebraic numbers which lie on a modular curve, one has exactly the same thing. Q of xy over Q. The degree of the point over Q is at least Cn to the delta. And this is going to be true for points that are not algebraic. If x is non-algebraic, then y will be non-algebraic, and they will indeed have, this will be just the full degree of the modular curve. I mean, it'll be a generic point. So this conjecture is somehow in line with expected bounds in Mordell's theorem. So Mordell's theorem would tell you about torsion points. So let me just write that down, because this looks, I think, when you write down this conjecture and then this conjecture, it looks a little bit, well, it maybe looks a bit too strong. But if you like, the Mordell uniformity theorem says that if you have an elliptic curve over a number field K, which has degree at most D, then the size of the torsion group of K points is at most N of D for some N depending only on D. And what that's telling you is that the modular curve Y1 of N has no points somehow that for large n, or for small n, there's no point for large n of degree less than or equal to D. I'm sorry? Except for the cusps, yes. Yes. No, except for the cusps. Maybe, well, all right, except for the cusps. But I didn't compactify my curve. Anyway, so if xy belongs to y1n, then qxy over q is at least D. It doesn't have points of small degree. And so Mordell just proved that there exists an n depending on D, but it seems to be a folklore conjecture that n is actually so the known bounds are exponential, but it's somehow believed, I've seen this written, that it's a polynomial in D, and so this is essentially the same kind of question on a different family of curves. Also, the gonality, the degree of a smallest map down to the projective line, the gonality over C of phi n of xy, is some positive constant times n. And so by a theorem of Frey based on Folting's big theorem, this curve can't have infinitely many points over a field of degree less than or equal to a small power of n. But of course, these other kind of conjectures say it's not that there really are no points up to a certain degree. But just to say that it's, well, there's this hierarchy of conjectures, and even this one where there's no curve whatsoever is not crazy, and indeed is sort of in line with other things that people believe.
Do we know more about Cn points for the question mark conjecture? If you take xy to be special.
Yes, I think I want all these points to be non-special. There exists, yeah. It'll be probably true.
Might be more studied, more well known.
Maybe for special it's known, but
No, the problem with special points is that they lie on too many special subvarieties. So if you choose a large, you've got infinitely many choices for the T. Somehow, you could choose a very large modular relation. So you'd have to take the minimal one, and then it should definitely then it is true. At least in this case on. Right? on Siegel's theorem and all of that. If they're special, it certainly is true. But I did mean non-special. Right. So now I want to talk a little bit about isogeny estimates. Maybe we'll do that here. Isogeny estimates.
Something I didn't get is that you said it was somehow so how it relates to LGO. I mean, because LGO is for unlikely intersections, but you say that this is
No, if you knew this, then that would certainly imply that, because you could view your unlikely intersection as, right, you project onto two of the coordinates, you've got a modular relation, you get at least this degree. You project onto the other two coordinates, you get at least the other one, and so you get at least the maximum.
Okay, so you're in the case where you can always find likely intersection from unlikely.
Yes.
Okay.
Yes.
I was not aware.
No, well, yeah, in the modular, everything product of one-dimensional things and two, the special relations are always pairwise. So yeah, this So these are in increasing order of strength. If you can get a bound on the degrees of likely intersections, you certainly get it on unlikely ones. And if you get a bound without any curve in the picture at all, then. So, isogeny estimates. So this the Masse-Wustholz. All right, but so I'm going to state a theorem, and in this very precise form, this is due to Gaudron and Raymond. So let E and E prime. All right, so I'm stating it in a precise, there's a very precise, very precise version of the isogeny estimates due to Gaudron and Raymond, but I'm stating them in a less, I'm not going to tell you what all the numbers are. Okay, they've got actual numbers, 10 to the 7, whatever. So, okay, so I'm stating it in a less precise form. I think it's kind of bad form to do that in a way, to claim it's someone's theorem and then state it weakly. But, right, so they stated, so this is, well, so these are elliptic curves. So I'm not stating it in the very precise form that they do it. So they're elliptic curves over K. K is a number field whose degree is at most capital D, and where D is at least 2, because we want to, well, that's to make the estimate work. And maybe I want, okay, if E and E prime are isogynous, and this is over the closure, there is an isogeny of degree n prime bounded by some constant which they make fully explicit, d squared log d squared, and the maximum of 1 and the height of the J invariant of E squared. Okay, so this is the isogeny estimate. It estimates the degree of an isogeny given only that one exists between these two curves and, well, this numerical information. And these kind of estimates grew out of Baker's theorem. This comes from an observation that when you do estimates in Baker's theorem, that they'll tell you of independence of logarithms, that if there is a relation, you can get one and control its height. And it's crucial here that only one of the height of the J invariance appears. The other one just doesn't appear. And a corollary, because this is a general isogeny, whereas in this business here, the modular polynomials control cyclic isogenies. So we can just write that down like this. Suppose that xy is a point on the modular curve where xy are algebraic and non-special. And let D be the maximum of 2 and the degree of the number field, then N is at most this. So this is almost the same statement by taking them. So with x and y non-special, if there's a cyclic isogeny between the elliptic curves whose J invariants are x and y, and the cyclic isogeny is unique because the points are non-special. On the other hand, there is an isogeny, some isogeny of this bounded degree here, but all the the maps from E to E prime are generated by any cyclic isogeny, and so this n is at most that n prime, the cyclic one. Right. And now the point is that if the height of the point is somehow negligible compared to these other quantities, then you immediately see that this d has to be basically the square root of n. You get a positive bound for the degree in terms of you get a lower bound of a positive exponent in this degree of the extension in terms of the degree of the cyclic isogeny, provided only these heights are negligible. That's the key point, and so now we can make some conjectures that are instead only about heights. But let me first consider, let's return to a curve V in y1 cubed with a constant coordinate. So this case is the one that falls in between the cracks of the assumption we made that V is not contained in any proper weakly special, and the right assumption is that it's not contained in any proper special subvariety. So let's suppose that V is this it fails the stronger condition but satisfies the weaker one. So it has a constant coordinate which is not special. And let's say it's x. And now the point is that the height of x, whatever it is, will eventually be negligible against all the n's and d's. So if you now have your unlikely point, if x, y, and z belongs to V intersect some special t defined by an n and an m, then that means that y and z I mean, this is by definition, in this case, this means that y and z are in the Hecke orbit of x. That's what it means to be in the Hecke orbit in y1. And because x is fixed, its height is eventually negligible. So once n gets large, the degree of the field xy has to be large. You can also view that as Serre's open image theorem on the image of GL2Q. And that means that in this case, we do get exactly the kind of bounds we want, and we can just repeat the proof, and you just repeat. And in fact, you're just looking at, so x is fixed, so you can now consider y and z. You're really on a curve, let's call it v prime in y1 squared, and you're looking for points y, z, which are in the Hecke orbit of x, or of x comma x, if you like, in the Hecke orbit of xx. And then this is a case of the Andre-Pink conjecture, where you intersect a variety with a Hecke orbit. And in this case, as I say, you immediately get your large Galois orbits. So this is a case of Andre-Pink and which actually has recently been fully proved in Shimura varieties of abelian type by Richard and Yafaev. But from our point of view, right. Now let me say at this point also that this same and we'll come to this a bit, but this same kind of reasoning helps you deal with what I've called here the type 2 intersections, where one coordinate is special and the other two have a modular relation. And the reason now is that the special point does indeed have negligible height as compared to the discriminant, which we'll still maybe see. And then the points y and z, because they're on a curve, their height is controlled by this one, which has small height compared to that discriminant. And so they all have quite small height compared to the complexity of this t, and the proof again goes through. So really the bad case in this type 3, where you just intersect with an n with a special subvariety defined by these two modular polynomials, your bad case is that every time you choose a new n and m, you get an intersection in which all these heights are really huge. So if you can't control those heights, then you can't control those degrees, at least not through that way. So this fits into the picture of the bounded heights in these problems. So I want to talk about Haberger's weakly bounded height conjecture. So that's a conjecture of Haberger. So let v in y1 squared, v defined over q bar and not special. There is a constant depending on v, positive, such that if xy is a point of v, which lies on a modular curve xy equals 0, so this is again a likely intersection, right? So this is likely intersection. Then the height of x and y to like just the maximum of those logarithmic absolute V heights is at most this constant times log of 1 plus n. So here n is at least 1. And Habegger proves that this would be best possible up to the constant. You simply do get likely intersections whose heights grow. This is the logarithmic height, right? So, I mean, you're allowing, because, well, at various points in these lectures I've used the multiplicative height, which is the exponential of that. It's not a very small bound, is what I'm trying to say. You're allowing height right up to some power of n.
There is a kind of Bezout theorem with heights in Markov theory. I suppose that in average it's this kind of thing. If you multiply by the number of
yes.
the degree of the intersection.
Yes, I guess it must be, yes. Yeah, so the key point is somehow whether those...
Almost all the same.
Well, yeah. Well, or whether they're all conjugate and over a large field, or whether they're all over, yeah. So this is somehow by analogy with bounded height in GM and abelian varieties. So in the case of GM and abelian varieties, Habegger proved the bounded height conjecture formulated by Bombieri Massezania, who proved it for curves. So that's a theorem of Habegger. So let V in GMN, or it can be an abelian variety over Q bar, I guess, since we want heights. The height of likely points is bounded outside what they call the weakly anomalous locus. The weakly anomalous locus means the union of positive dimensional unlikely intersections with weakly special subvarieties. So this is some closed subvariety. And then with this theorem, Habegger could then prove the most general results that are known on Zilber-Pink in GM and abelian varieties. What he is saying, you then prove that outside of this weakly anomalous locus, V, I think they called it VOA, the open anomalous. So outside of that locus, you can only have finitely many unlikely intersections. So that's exactly the finiteness you want, and all you would want is to have it outside the, the unlikely intersections with special subvarieties instead of weakly ones. However, on the anomalous locus, the height is not bounded. On the weakly anomalous locus, height is not bounded. And maybe the simplest case of that is simply if you take xy equals 2 in GMN. So that's a weakly special, that's not special. And if you intersect with specials of the form x to the m, y to the m minus 1 equals 1, you'll see that you'll generate points that have unbounded height. It's simply not bounded on the anomalous locus. Ooh, right. And so, yeah, so if you like, in the modular and Shimura settings, you do not get bounded height, even sort of in general, but you can expect perhaps weakly bound. It's not, I mean, the weakly bounded isn't bounded, but it's a bound that's, well, it's weakly bounded in terms of this. But of course, this, which is essentially best possible, is much more than you need. So I think we call this the super weakly bounded height, can maybe Habeger. Super weakly bounded height conjecture would be enough that if, so again, V is a curve in y1 squared over q bar, not special, and epsilon positive, then the height xy of a likely intersection, phi n x y equals 0, then the height is at most constant depending on epsilon n to the epsilon. That would certainly do in right, because in this isogeny estimate, if you put here n to a very small power, you can then sort of deduct that over here, over here, and you get the degree is positively bounded. So in fact, you win provided epsilon is less than a half. So even any epsilon less than a half would do. Then you could get some traction between D and N. But the known bound, which follows from Paula Cohen's work on the height of modular polynomials, is n to the 1 plus epsilon. And so you just get nothing in that. You get nothing useful. All right. So, okay, so I've sketched this unlikely problem in y1 cubed. I just want to say that Zilber-Pink problems in, right, so one of the points, I mean, that's all erased now, but one of the points of the method is that your unlikely intersection gave rise to a rational point on this other set parametrizing weakly specials. And more generally, if you look at Zilber-Pink in a mixed Shimura variety, then the unlikely intersections will always lead to some rational points somewhere, because the mixed Shimura variety is defined by Q groups, and the weakly specials are defined by suitable Q subgroups. And so point counting is a kind of plausible approach, provided you have some reasonable expectation that the points you're looking for have large Galois conjugates. And so while it looks good for some problems, and it has indeed been made to work in quite a few different situations, it's somehow ultimately not useful, let's say, if you were trying to use this technique to do something like the Mordell conjecture or Mordell-Lang, because when the points involved are rational, they don't have Galois orbits. Or they have Galois orbits, but they're very small. Now, so you can phrase this, I think I talked about Zilber-Pink in terms of optimal points. So you can frame Zilber-Pink in terms of studying the optimal subvarieties of a given variety contained in some mixed Shimura variety. And you can even reduce to studying the optimal points, because the higher dimensional things will come from optimal points somewhere else. So you can reduce to studying just optimal points. If you can prove finiteness for optimal points, that means a point on your variety which is unlikely and which if you consider it on any larger subvariety of your variety, the defect goes up. It's less unlikely. So you can show so Habegger and I did this in y1 to the n. We showed that Zilber-Pink reduces to a large Galois orbit conjecture for optimal points. You've got the same complexity. If you have an optimal point, you look at the special it's in, you measure it by the complexity, and you simply ask that the optimal point has a large degree. And so Dorr and Wren have done this more generally for Shimura varieties, that essentially by a point counting argument, Zilber-Pink reduces to a Galois orbit, plus some other conjectures of this height ingredient type that they didn't fully deal with. And my student Kasani has extended that to mixed Shimura varieties, but just again to keep in mind that if you postulate that optimal points have a large Galois orbit, you're sort of building in anything that looks like the Mordell conjecture, right? Because you're saying that a large rational point can never be optimal because it would have no Galois orbit. On the other hand, Mordell-Lang is, of course, a theorem, and so in some sense, that problem is dealt with. Okay, so this picture can be applied much more generally. If you like, in a conjectural way, if you assume some kind of large Galois orbits. Oh, but I guess I didn't say, yeah. And as I've sketched, you can actually, I don't know where I was going to say that, but you can make this work in some cases. So again, Habegger and I did this case, which if you like is the intersection with non-strongly special subvarieties. And we did a case where the curve has a non-generic condition of being asymmetric. And I know I had it somewhere on my notes, but I don't find it. Dorr and Wren prove this Zilber-Pink for a curve provided it goes through the point infinity, infinity, infinity. In other words, that there's a point of a multiplicative reduction of the three elliptic curves, and Papas generalizes that further, and that uses, so I should say that Dorr, Wren, and Papas have results that use the theory of G functions, which is somehow the right tool. That if you have these unlikely points, you get exceptional relations on the periods of these elliptic curves, and then you can use this Andre-Bombieri theory of G functions, again to control the heights, and you can get some results. I don't know, I had that in my notes, and I don't know, I managed to not say it. I wanted to say so that's what I wanted to say generally about point counting and Zilber-Pink. So this kind of approach can work conjecturally quite well, and also in various special cases. And you always have these various ingredients, the height ingredients and the functional transcendence stuff. And generally speaking, things come down to either the Galois orbits or the heights of the exceptional points you're looking for. So I wanted to just end by saying a little bit about uniformity in these problems. So let's just say something about O-minimal uniformity. The point being that results in O-minimality tend to come with uniformity in families. If you have a family, an algebraic family of varieties, then you'll get the definable sets you want to count in will be in definable families, and you'll be able to parameterize them uniformly. So we saw that counting is uniform in definable families, just fully uniform. So if you're, for example, considering the Andre-Oort conjecture, special points do have large Galois orbits, and of course that's independent of what variety they're sitting on. And the only issue is how many conjugates you lose when you take conjugates, and that's only to do with the degree of the field of definition of V. So now I can make a definition for V subset of X, mixed Shimura variety. I can let special set of V denote the union of special subvarieties of X varieties which are subsets of V. And then the Andre-Oort conjecture is exactly saying that that's a finite union of subvarieties. So then you can, the uniformity tells you that if you take n, d, and k positive integers and consider an algebraic family, let's say V, parameterized by some c to the n in y1 to the n of hypersurfaces of degree d in c to the n, y1 to the n. And you consider, so then if you consider, well, there are only finitely many possibilities for the special set of the hypersurface with parameter p if Vp defined over a number field K with KQ less than or equal to little k. Right, so you just consider the family of hypersurfaces all of the same degree. That's a definable family. And if you also restrict the degree of the field of definition, then you'll get, well, the Andre-Oort conjecture in a very uniform way. There's only finitely many possibilities. And the same in any Shimura variety. So, of course, one thing I haven't really addressed at all is effectivity. Well, I simply haven't addressed it all. But of course, counting is uniform, but it's in general not very effective. And the lower bounds for Galois orbits aren't effective either. So in general, results, Andre-Oort results, are not effective. An exception is the result of Kuna and Bilu-Massa-Zanya on effectivity in Andre's theorem, and also some curves in A2, the moduli space of abelian surfaces due to Bignamini massa. But let me write down an effective theorem of Kuna. So, okay. Epsilon is positive, and delta and d positive integers, then he says there exists an effective constant C epsilon delta and d positive with the following property. Let v in y squared geometrically reducible and over a number field k with kq less than or equal to d, and apologies for using different letters everywhere, and delta be the maximum of the degrees of the coordinates of those maps down to C, the coordinate maps. So this is the xi restricted to V as a map down to C. I equals 1, 2. Then he says the maximum of mod d1 and mod d2 is less than or equal to our constant times the max of 1 and the height of the variety to the power 8 plus epsilon for every special point, for special point of discriminant d1, d2 on V, not lying on a modular curve Tn, which is the modular curve defined by phi n, with n less than or equal to 4 delta to the 5th. So that's a very explicit and effective statement. And I guess the thing I wanted to point out is that from an O-minimal point of view, this bound shouldn't depend on the height of the variety. But this is an effective theorem, and it doesn't use these tools. This theorem uses linear forms in logarithms and elliptic logarithms, but it's kind of interesting that, it gets you that extra dependence. Right. Now, so that's O-minimal uniformity, but I wanted to talk about uniformity more generally. So if instead of considering hypersurfaces or even curves in y1 squared, if you drop the requirement that your curve or hypersurface is defined over a number field, then you cannot hope for any uniformity of this kind because, of course, you can move your curve around and stick it through any special point that you want. But you can get a uniform bound on the number of special points. And this, in Andre-Oort and Manin-Mumford and Mordell-Lang type problems, this is the principle of automatic uniformity. You can see a paper of Tom Scanlon where he proves this. He gives a model-theoretic proof of this fact, that the form of these statements is such that if you take, let's say, a family of curves or of hypersurfaces in y1 to the n, or in fact in any Shimura variety, then you get a numerical uniformity on the special points and even on the special set. If you say in one ambient variety. And I say that, I mean, this is more natural to do. In Shimura varieties don't have moduli, so there's no natural way to vary them, but abelian varieties do. And so while you get automatic uniformity for things like Munn and Mumford, in a fixed abelian variety, let's say if you take all curves in an abelian variety, all varieties of a certain form, then the special sets of them will all be the number of isolated special points, the number of them will be bounded, and also the special sets in a way I will explain. But this kind of automatic proof doesn't work if you vary the abelian variety. So let's say CF, the very recent uniformity results in Mordell-Lang and Munn and Mumford of the papers variously by Dimitrov, Gao, Ger, Haberger, and Kuhner, which I'll come back to in a little bit. So what this kind of automatic uniformity means is that in a family, let me write it in an algebraic family, V sub p of subvarieties, which could be like this family of hypersurfaces or any algebraic family, that the special sets, well, there'll be some finite and bounded number of special points, and then the rest will be translates of some finitely many strongly special things, which are also of a bounded number of those things appear over the family. So a way of saying it, that is that the special set of any VP is some WQ, where WQ is also some algebraic family. So in the simplest case, if you're a family, some family of curves in y1 squared, and this is just the number of special points, then this is just saying that the number of special points is uniformly bounded, so it's equal to some fiber in the family of, 10 points in that variety. So one can express this automatic uniformity, which holds in Andre-Oort and Munn and Mumford and Mordell-Lang, as saying that the special set, that in an algebraic family, the special sets are also fibers in some other algebraic family. They're bounded as cycles, if you like. They're in some algebraic family of cycles. And again, this is for a fixed ambient. But now I want to talk about uniform Zilber-Pink. And again, we can recall that Zilber-Pink can be expressed as saying that the set of optimal subvarieties of V is finite. Right, that the set of optimal subvarieties for V in an X, the set of optimal subvarieties is a finite set. So you can also consider it as a cycle. And they do come from finitely many families and so on. So I guess I don't want to, and again, to prove Zilber-Pink, it's enough to prove this for finiteness of optimal points. Again, the optimal points are the unlikely points that are sort of minimal defect among all subvarieties of V, the difference between the point and the dimension of its of the smallest special subvariety enclosing it. Right. So that's all just to somehow to say that it seems that Zilber-Pink also implies its own uniformity. So again, Scanlon gave a sort of model-theoretic argument, but you can view this as applying, if you want to do this for Andre-Oort, you can set up an incidence variety of all the points on 20. You can take 20 copies of X and look at all the points in there for which there's a P for which all the 20 points lie on one of the VPs. And then you apply Andre-Oort to that, and you can eventually deduce the boundedness, this property. And you can do a similar thing with Zilber-Pink, which Zanya sketches for the uniformity in curves in GMN. And I worked this out more generally in the modular and multiplicative cases, that, if you like, Zilber-Pink implies what you would call uniform Zilber-Pink in GMN and y1 to the n. And this uniform Zilber-Pink means that in an algebraic family of varieties, the set of optimal subvarieties considered as a cycle are also in an algebraic family. They're sort of bounded as cycles. And the same presumably holds in general. It's kind of interesting. It ends up using some kind of Ramsey-type principles to say if you have a lot of things, you must have also a large number of the same type. So it's kind of, well, it presumably works in general, but it would take some, a little bit to work it out. And again, and this is consistent with the results of Dimitrov, Gao, Gerhaberger, Kuhn, which would say, for example, that if you bound the dimension of an abelian variety and the rank of the Mordell-Weil group, and you take curves in an algebraic, if you take subvarieties in an algebraic family, then you do expect an absolute bound on the number of rational points or the number of subtori. And which had been, I think that implication that Zilber-Pink implies this kind of uniformity had been worked out by Stoll. Of course, they get the uniformity in a very strong, in terms of the form of dependence, is also very strong. But I just wanted to touch on those uniformity aspects. And I think that's really all I wanted to say. So thank you very much for your attention.
Any questions?
What happens in the case of asymmetric curve?
Yeah, in an asymmetric curve, the difference in the degrees of two coordinates on the curve, and the fact that they're on a curve means that there's a height relationship between the different coordinates, but the isogeny estimates say that the heights have to be very close. And you can sort of exploit the tension between those two things to prove that the height has to be small. Otherwise, there's a sort of...
This is an interesting case.
It's an
interesting case.
Yes. Yeah, no, but it's a non-generic condition, so unfortunately, yeah. In a way, the G-functions approach looks like the more natural approach because this whole subject, the Andre-Oort, it all starts with Andre's book on G-functions. That's where he made that conjecture. And it's all comes out of the heights of these relations on periods and what you should expect. And that does seem to be most natural approach. But the asymmetry then with more crude properties of heights and the fact that isogynous elliptic curves have very close heights, which I didn't write down, but I mean that's also very I guess that goes back to faultings, maybe, the fact that the height, if you have elliptic curves or abelian varieties that are isogynous, their heights are very, very close. That's sort of a very classical thing, but I didn't, yeah.
If you consider heights intersection degrees in arithmetic schemes, are there analogs, large Galois big conjecture, which would be large height conjectures?
You mean small height or large height?
Like values, you imagine you take Q-bar points.
Yes.
You apply modular polynomial or secret unit polynomial to it. You assume it's not a root of unity. You make the n of this number goes to infinity. And you would like the height of the value at this Q-bar point to be high.
Yeah, I don't know. As you say, I mean, it all comes down to, well, understanding those kind of intersections. The problem there is that the modular polynomials, well, are not an algebraic family. And, I mean, so you're sort of.
Yeah, that's similar to that.
Yeah, but I guess I don't know. It's certainly interesting to think about how those intersections look somehow in general. Okay.